Hello guys, welcome to the next section of tutorials on review of probability. Now in our earlier discussion we looked at the definition of probability space, and then we looked at conditional probability, Bayes rule, and then we looked at the idea of independence, we looked at the idea of random variables, different kinds of random variables. We saw discrete random variables, the CDF, the cumulative distribution function, how is it defined and what are the properties that cumulative distribution function should satisfy. And then we looked at for a discrete random variable, how does the PMF, the probability mass function, is being defined and what are the properties that the mass function has to satisfy. And then we looked at different kinds of discrete random variable by like Bernoulli distributions, binomial distribution, geometric distribution, so on and so forth, and how does the PMF for each of those cases are defined. And then for a discrete random variable, now it is to completely specify the random variable. Now either if we are given the cumulative distribution function or the mass function, it would be it completely specifies the things. Okay. So now we will continue our discussion with the another kind of random variable that we are looking at now, which is the continuous random variable. Okay. Now that is what we will do. We will look at the continuous random variables and then a couple of examples of continuous random variables, and then we will look at the functions of random variables followed by expectations and variance. Okay. Now this is what this section of tutorial is outlined with. Okay. So now without further delay, let us proceed. So now a random variable x is said to be continuous or continuous type if there exists a function, px, okay, which is this is called as the PDF, the probability density function, which is an R2R function. See, and then here I just want you to understand that this is the same notation is being used even for PMF, the same notation will be used for PDF. Now depending on the type of random variable, you should be able to distinguish what is what. Okay. So there exists a function now px, which is an R2R function, such that the cumulative distribution function at that point is integral of minus infinity to x. So whatever x that has been considered into the density, the integral of the density function which is there, okay, at that point for all x. Now this has to be true for all x. So the PF which is there is what is known as the probability density function of x. Okay. So now if x is a continuous random variable, by definition, okay, this is for all x, okay, by definition the distribution function which is there will be continuous at every x. Okay. I think it which is pretty much clear to see from this definition. And the fundamental theorem of calculus will directly show us that you take the derivative of this distribution function, you get the density function for all x wherever this the density is continuous. Okay. So now continuous random variable takes uncountably many values. Okay. If a random variable takes uncountably infinite many distinct value, it is not necessary that it implies that the type of random variable that we are dealing with is of continuous type. Okay. So just because a random variable we have an RV, if we have a random variable that takes uncountably infinite many distinct value, so does not necessarily imply that this is a continuous type random variable. Okay. So now the distribution, now this is from the right side, this is from the left side. Okay. Now these are same. Now why? It is continuous at every x. Okay. Now therefore the px of any given x which is there now will be 0 for all x. Okay. And what are the properties that the PDF should satisfy? Now it is an R2R function which is there, it has to satisfy these things. For all x which is there, it has to be greater than 0, and then you integrate from minus infinity to infinity, you should get 1. And see, now here you can see the similarity between the PMF and the PDF which is there. See, instead of this integral which is integrating over minus infinity to infinity which is there, now what you will have summation over all the valid values that it is taking, that also should sum to 1, okay. And then each of the mass at each of the elements which is defined, so has to be greater than or equal to, it has to be between 0 and 1. Now that specific restriction is not here, okay, that is the difference, okay. Now please note those differences. It has to be just to be greater than 0, it is not saying that the PDF value should be between 0 and 1, okay. So that is not being said, that is the reason why we say that the PDF is not a valid probability measure. On the other hand, the CDF and the PMF are actually valid probability measures, okay, fine. Any function that satisfies these two above conditions now has to be the PDF of a continuous random variable, okay. Now therefore, now Px satisfying the above, and because of which what will happen in this continuous case, the CDF of minus infinity will go to 0, of plus infinity will go to 1, which is straightforward. Minus infinity to infinity, if you put, now if it is a valid PDF, now it has to be 1, therefore the CDF at infinity will be 1, and Px is non decreasing and Px is continuous. See the difference here. Now the standard definition that we wrote at that time was it has to be right continuous with left limits, okay. But now because we are assuming a continuous random variable, what happens here is, since at all the x it is continuous, so this the Px, the distribution function, becomes continuous, okay, fine. Now if you want to know the probability at an interval, okay, of an interval AB, now it will be the CDF at B minus CDF at A, okay. So now for a continuous random variable, the probability of all x, okay, if you take what is the probability at a point x, it will be 0. Please remember that this is for all x, okay, fine. And then whether you include a point, whether, so it is like whether, so A less than or equal to x, or A is just less than x, or here you do not have the equality. In all these cases, see what is the difference between this and this. Now for this you would have added probability x is taking the value of A, x taking the value, any value is 0, therefore these two takes the same value. Now what is the difference between this and this, okay. It has one element which is probability x taking the value B, which is an additional thing, since it is 0, now all these intervals, now inclusion of equality at any of the interval is same, okay, fine. So we normally write it, we put the less than or equal to in all these cases, so it will be the integral of the PDF in that interval AB, okay. So this is the definition of continuous random variable. Now let us go ahead and look at some of the examples of continuous random variables, the first one being the uniform distribution, okay. So x is a uniform over an interval AB when the PDF is defined by this 1 over B minus A for all the x which is between this interval A and B. For any x that is not in this interval A and B, it will be 0, okay. So now from our previous discussion, it should be pretty much clear that uniform distribution over open closed interval is essentially the same, okay. From our previous discussion, it should be pretty much clear that y is this, okay. Now this is a simple example. I have taken uniform over 0 1. So whenever it is uniform, 1 over B minus A will be the PDF. What is the value of B? 1 minus 0. Now therefore for all the values between 0 and 1, the PDF will be 1, okay. Now how will be the CDF? Now CDF will be x for all the values between 0 and 1. For every x that is less than or equal to 0, it will be 0. For every x which is greater than 1, no, it will be 1. Therefore you can see that this will be the CDF and then this will be the PDF. Okay. Now I have referred here. So this is very much easy to see it from here. Okay. So the next kind of distribution, that is the exponential distribution. We will sample from each one of them. So in our the next what do you call, in couple of minutes we will be getting samples from each of these distribution, and then we will be plotting the histograms. Now till then I will just mathematically define these things properly first, then I will go into the coding aspects of the same, and how do you sample from those distribution. I will show it to you using NumPy. Okay. All the categorical all the discrete distributions and all the continuous distribution that we will be seeing, we will be actually working them over the code as well. Okay. So the PDF of exponential distribution is this. Okay. Just rather than reading it, so this is evident. So x has to be greater than or equal to 0, and then this lambda which is there has the parameter of this has to be greater than 0. Okay. And the PDF is equal to 0 for all x which is less than or equal to 0, and it is easy for us to verify that if you integrate this PDF which is there from minus infinity to infinity. So minus infinity to infinity, you can break it into two things, minus infinity to 0 is 1, and then 0 to infinity, and minus infinity to 0, no, this will become 0. Why? There are no valid values over there, no, in the sense all the values are taking 0. Okay, and 0 to infinity is what you have to consider, and then you integrate this specific thing from 0 to infinity, you get 1. Okay. So and then how will be the CDF looks like? Now it will be 0 for all x which is less than 0, and then the CDF will be 0 to x at this point, which is 1 minus e to the power of minus lambda x, which is that. Now for exponential distribution, this is the PDF, and then this is the CDF. Then the king of all distributions, no, it is not explicitly referred like that, I am just telling that because we will be using this most of the time. So therefore you can think of this as a king of all distributions. Gaussian distribution, or known as the normal distribution, is the PDF is defined by this 1 over sigma into square root of 2 pi exponential of minus x minus mu whole square divided by 2 sigma square. Now wherein which mu is the mean, and then sigma square is the variance, and sigma is the standard deviation that is there. Okay. And the sigma which is there is greater than 0, and the mu is a number. Okay. We are still considering only the scalar valued random variables. So we will come to vector valued random variables in some time, maybe in next section of the tutorials. Okay, fine. So we represent this x is from normal mu and sigma square. This is what is known as the normal distribution. In the case if you take mu is equal to 0 and sigma square is equal to 1, this is what is known as the standard Gaussian or standard normal distribution. Okay. Under the conditions that mu is 0 and sigma square is 1. Okay. Now these are couple of examples of continuous random variables, continuous type random variables. Now let us look at a very important thing and very interesting thing that is needed for us most of the times, is what is known as the functions of random variables. Okay. So now here let x be a random variable on some probability space omega fp. Now x is from omega to r. Okay. Now consider a function which is r to r. Let now y is equal to g of x, then y also maps from omega to real line. So you can see this is omega, this is x, and then you have g which is from r to r. Okay. And then you define g of x. Now in that case x is mapping from omega to r, you use that r and then you map to another r which is there. Okay. Now therefore you can compositely you can think of y as mapping from omega to r. The standard example that you can think of is like for example so okay so a bit of a lengthy example to think. So you go to a hotel, and then you can take one item, so that is the condition in which we are dealing. So you can think of this as the what do you call the billing, okay, and then this bill you are paying it from your what do you call from your UPI, and then because of which there will be a change in your what do you call money in your account. Now therefore you can directly think of this as a composite function, now relating your sample space to the reduction in your account, okay, something like this. This is a very straightforward and a simple example which you can ponder on, okay. Now if G is a nice function, okay, I have put in nice, what does that nice mean, I will go ahead, okay, then Y would be a random variable. So now any random variable, now you should have cumulative distribution function. How do you do it? Now cumulative distribution function of this random variable Y for considered for a given Y is probability that Y takes the value Y less than or equal to the considered Y, okay. So and then what is this capital Y? Capital Y you can consider the capital Y now, which is nothing but the G of X now, which is there, okay. Now and then that you can immediately sorry, so that you can immediately write that X, what are the X's that you are considering? X belongs to all those elements Z for which G of Z is less than or equal to Y, which is just the reverse mapping that we have seen earlier, okay. So now this probability can be obtained from a distribution of X, okay. In principle we can find the distribution of Y if we know that of the X. If you know the distribution of X, you can easily find the distribution of Y. An example here, if Y is equal to AX plus B and A is greater than 0, now this is the definition of CDF. Now Y is AX plus B, now because of which you can write this whole thing as X less than or equal to Y minus B by A, and if you know the CDF of X, now you can directly write this. That means that now we can obtain the CDF of Y if we know the CDF of X. That is what is being discussed here, okay. Now comes okay, now you can obtain the CDF, well and good. How do you get the PDF? Okay, most of the times we will be working with continuous random variables, okay. So now this is a very useful theorem as we go along. The name of the theorem is change of variable theorem, okay. Now it has certain conditions. Let G be an R2R function, be differentiable with, so G dash of X is greater than 0 for all X, or G dash of X is less than 0 for all X, either it has to satisfy one of them, okay, for all X. For some it is greater than 0, for some it is less than 0, no, for all X that has been considered. Let X be a continuous random variable and let Y is equal to G of X, and then Y is a continuous random variable with this as its PDF. Now how do you define this PDF of Y? Now it is, you take the PDF of X at this the inverse value which is there, okay, and then you take the absolute value of this, okay. And what will be the valid values for Y, now which is A and B? What is this A? Now A is minimum of G of infinity and G of minus infinity, and B is maximum of G of infinity or G of minus infinity. Now this is what is known as the change of variable theorem. Now that means that if you know the PDF of X and then you know the function G, now you can if you have Y is equal to g of x function which is there. Now you can obtain the PDF of y using the PDF of x, and why is it PDF needed? All of us know why. Okay. This is a very useful theorem, we will be using it multiple times during our discussion. Okay. I hope you please look at this and then please remember the conditions in which we can use this change of variable theorem. Okay. Now let us move towards the expectations. Okay. The expectation of discrete random variable. Let x be a discrete random variable which take these values. Okay. We define the expectation like this, scripted E of x. So you sum over I xi into its mass. Now you can think of it like some kind of a weighted average of each of the thing. Okay. Now weighted by its mass. Okay. This is how I define the expectation for a discrete random variable. Now how do you define it for a continuous random variable? My extension is pretty much simple. Use integral, you integrate it over minus infinity to infinity x into the PDF. Okay. Now this is a for a continuous random variable, therefore this symbol represents the PDF of it. Okay, PDF. So sometimes we do not use this brackets, we just write Ex like this. Okay. And please remember that this is a scalar in the current case. So we have only looking at the scalar valued random variables as of now. Now therefore it is a scalar. Okay, it is a single number. Please keep that in mind. Okay. And couple of values for binary random variable, which is our Bernoulli trial, which is expectation of x. It takes value 0 and 1, 0 into the mass of at 0, 1 into the mass at 1. Now this goes off, this is probability of it's taking the value 1. Okay. And the same thing, expectation of indicator random variable is the probability of the event that it wants to indicate. Okay. And similarly you can obtain it for Poisson random variable, geometric, binomial, uniform, exponential and Gaussian distribution. I have just put it as a list. Now another important thing that is needed for us is the law of the unconscious statistician, or known as the lotus. So now how do you take the expectation of a function of a random variable? We know how to take the expectation of a random variable, we know how to do it. Now how do you go ahead and take the expectation of a function of a random variable is what we are looking into now. Okay. Let x be a random variable and let y is equal to g of x, this is the function. Okay. We have defined the function on random variable already. If x is discrete, okay, the expectation of y, how do you take the expectation of the function of the random variable? X is the random variable under consideration, y is the function of the random variable. How do you compute the expectation of the function of the random variable? Okay. So now the sum over yi into py of yi. Now what is this yi? Now yi is g of xi and this is px of xi. So that means that now unconsciously, so why it is called as unconscious statistician is, so not someone is unconscious sleeping, no, unconsciously you apply, you just apply the for each x, you unconsciously you just apply the transformation which is there and take the mass as it is. Okay, that is why it is called as unconscious statistician, not that he is sleeping and he is unconscious, no, you can apply it unconsciously, you do not need to think through it. Okay, see now it might feel like a very simple theorem, but the proof goes around 3 pages for this. Okay, I urge you to look out for the proof. And if x and y are continuous, now then an extension you integrate it. So integration minus infinity to infinity. Okay, so this is gx into the density of it. Okay, this is what is known as the law of the unconscious statistician or lotus. Now some of the very important properties of expectations, which we will be using left, right, center, everywhere, wherever you see expectations we will be using this. Now if x is a positive random variable, that is x takes value greater than or equal to 0, all the x takes the value, now then expectation of x will be greater than or equal to 0. Why? By straightforward, by the definition, if xi is only taking the non-negative values and this is between 0 and 1, okay, xi is taking only non-negative values and this is between 0 and 1, and you have a summation, this is positive, sum of the positive things or non-negative things will be positive, and similarly for this, similarly for continuous random variable as well. Okay. And then expectation of a constant, b is a constant, so expectation of a constant is the constant itself. Okay. Now expectation of a into a function of the random variable is you can take easily a outside and expectation of that function of the random variable. Okay. Now expectation ax plus b, now you can this is a into expectation of x plus b, an extension of it you have a g1x plus b g2x, expectation of that, expectation of this plus expectation of this, this is expectation of a into g of x, you can write of a into expectation of g1 of x plus b into expectation of g2 of x. Okay. So the linearity of expectations, so you can easily look out from here. Okay. Now these are very important properties to keep in what do you call readily in your head. Now we will be using these things also regularly. Now let us look at the variance of the random variable. We define variance of a random variable x as expectation of x minus ex. So see, you can think of it like this, see x minus ex is actually the deviation of the values of x from the mean or from the expectation, and then you take the square of it. You can think of it like, see, expectation can be thought of as some kind of an average, so you can think of it like an average deviation in terms of average square deviation, you can think of it like that. Okay. So now you can expand this, so you can expand this square. Now this ex is a constant, okay, it's a single value, that's why I told you, remember that ex is a single value. So x minus ex, you can expand this, and then because of linearity of expectations you can take it inside, and then you can solve for this. So variance of x will be expectation of x square minus expectation of x whole square. See, now you have this x square, this is a function of a random variable. Now you have to use, so to compute this expectation of x square, now how do you know how to compute expectation of x, but we do not know how to compute expectation of x square. Now x square is a function of x. Now therefore you can use law of the unconscious statistician and compute this expectation. So and then expectation of x you have already computed. Okay. So now see, this x minus ex now is there, you take the square of it, now this will always be the positive. So you can think of this as one some random variable y. Now y can only take the values which are non-negative. Now expectation of a non-negative random variable is non-negative. Okay. Now therefore, now that means that this is always greater than or equal to 0, the variance of x is always greater than or equal to 0. Therefore it directly implies that expectation of x square is greater than expectation of x whole square from that. Okay. And some of the important properties of variance. Now you have this variance of x plus c, you add a constant to all the elements of c. Now this is variance of x itself, okay, where c is the constant. Okay, you have just added the constant, the variance now will not change. Now if you multiply it, it will be c square into variance of x. Now I urge you to please go ahead and you can solve this. How do you do it? Instead of x you just put x plus c here, here also x plus c here, and then you can see that how does that c square gets off. Okay, fine. Now here you can see this. Okay. Now this is regarding the variance. So now we will be looking at some of the important inequalities. See, I will not be going ahead with any of the proofs of these inequalities. Now these proofs are easily available. I will not be going into any of the proofs of these inequalities. I will be just stating those inequalities. The first inequality that we will be needing is what is known as the Markov inequality. Probability of absolute value of x, now it is greater than c. Now this is less than or equal to expectation of x to the power of k, absolute value of the expectation of the absolute value of x to the power of k divided by c power of k. You can this is the Markov inequality which is there. And then an extension of Markov inequality under certain conditions is Chebyshev inequality. Now recall the Markov inequality, and then instead of the absolute value of x, you take the absolute value of x minus expectation of x, and k is equal to 2. Now in that case what will happen? This term will become the variance of x. Okay. Now it has to be square, but if you take the absolute value, this is minus 2 square and 2 square, both of them will yield you the same thing. So this and x minus expectation of x will yield us the same thing. Okay. So this will be variance of x by c square. Okay. Now this is the Chebyshev inequality under certain conditions, that again you consider that expectation to be mu and variance to be sigma square and c to be k into the standard deviation which is there. Now then the Chebyshev inequality now will turn something like this. Just substitute them, we will be able to get it. Okay. And please look at it here. So we are not specifically saying it for any one kind of random variable. Okay. So this is true for all random variables. So none of this depends on the kind of distribution or the kind of random variable which is there. Now then the inequality, the next inequality that we will be considering involves the function itself. So which is the Jensen's inequality, which we will be using quite a lot. So let G be an R2R function and convex in nature. I am assuming that all of you are very much comfortable about now what do you mean by a convex function and what do you mean by a concave function, how does they work, else please make a note of it and then you need to look at it. Okay. Then the g of expectation of x is less than expectation of g of x. Okay. So this is what is known as the Jensen's inequality. Now these three inequalities and much more, in these three we will be using this Jensen's inequality a lot of times in our discussions during the course. Okay. So I urge you to look at the proofs of them, very simple and interesting proofs, you can look at them. Okay. Now what we will do now is, now this is the what do you call, this kind of a completion of theory discussions. So now what we will do is we will look at the implementations of these ideas in the collab. Okay. Just a minute. So now let us go ahead with the demo of them. So for this we will be using the numpy. Okay. So we will be using the numpy and then the matplotlib is needed, and from the math I will be using this combination. Why do you need this combination? Remember binomial distribution to compute the PMF over there, factorials. Now why do you need factorial? Pi value is needed. Why? Your PDF of exponential, PDF of Gaussian distribution needs the value of pi. Square root is needed, square root of 2 pi. Now exp is needed, log is needed. These are the couple of functionalities that are needed in evaluating these values. Okay. So then I will be going ahead with RNG, which is random number generator. I will be using the default random number generator, now using the seed as 42. Now the seed is used for the reproducibility. Now you fix with some seed and then reproducibility become much more comfortable. Okay. So now then, now whenever we are going ahead with the precision, now we will be going till 4 points. Okay. And what is the version of numpy that I am using? The version of numpy that I am being currently used here is 2.0.2. Okay. Yeah, it takes some time to run this. Okay. Yes, done. Good. So now first let us take a very simple empirical estimation of the dice probability. Now the number of trials that I am considering is this, okay. Now you can either put a comma or put underscore, it is perfectly fine, okay. It is 100,000 is what I am considering. The number of rolls that I am considering is that, and how many faces are there in that dice. Now it has 1 to 6, we know why 7 we have written, okay. So now you can put the shape of this, so you will get a 100,000 length vector which is there. Now here, now let us the idea is, now I have obtained these many samples, I have obtained some 100,000 samples. I know theoretically now what will be the probability of each of the event. Now I have done these so many samples, right. Now with those many samples am I getting somewhere around the similar values is what I am checking here. Now probability of 4 is np dot mean or this dice roll wherever it is 4. Now that means that wherever it's calculating how many times these 4 has occurred and the average is being taken, okay. So now and even now it is the roll dice whenever it is modulus of 2 which is an even number it is taking, and greater than 3 the probability which is the probability that the dice, the roll of the dice gets the value greater than 3. Now these are and even and greater than 3. So these are the different probabilities that I am considering. I hope that you can this is probability that probability of 4, this is probability of even, this is probability that it is taking the value greater than 3. Now that means that now it is taking the value 4, 5 and 6, okay. What is the probability that it is taking, okay. So and then it is taking even and greater than 3. I am assuming that you considering that the dice is a fair dice, computing these probabilities will not be an issue for you guys, okay. I hope you pause this video at this time, compute these values, and then these are these values theoretically from the known formulas that we have discussed now, and then let us compare them with the estimated values that we are getting, okay. Now if I run this, you can see here probability of 4 is now it has to be 1 over 6, okay. You are getting 0.669 is what you are getting, which is almost similar to here, okay. Now probability that it has to be even, see now you have only 2 sets, either it has to be even or it has to be odd, so it has to be 0.5, so it is 0.499 is what you are getting, and then theoretical probability that it has to be even, you can see it that it is 0.5 which is known to us. So and then the estimated probability that x is even and x greater than 3 and that is 0.332. Now what are the values that x is greater than 3 and it is even? Now it is probability that it takes either value 4 or it takes value 6, okay. So now you can compute, you should have computed these probabilities and then you can compare them with the obtained estimated values, okay. So now a simple example to computation of Bayes rule. Now suppose that the probability of getting a disease is 0.01 is the prevalence of disease, and then let T positive denotes the positive test results, okay. And then we will assume that now the probability of T being positive given D, now this is slash mid is given, so you can have to think is 0.95, and then the test is positive given the disease complement, that is disease not existent, is 0.05, then now what is the probability that D given T positive, okay. Now how do you compute this is the question, probability that D given T plus. Now you can apply the Bayes rule, okay, and then you can compute it. So now probability of disease is 0.01, the positive P positive given the disease, this is P positive given no disease, okay, sum is 1, you can see that. Now how do you compute, this is P positive, now why the P positive has to be in the denominator, okay, and this is disease given positive is positive given disease into positive disease divided by the p positive, and this is, you can immediately see that this is using the total law of probability. You have computed this, okay, and it is very much easy to see that the possibility that you have a disease giving it is positive is this value, okay. This is just a numerical application of Bayes rule. So I want you to compute this in hand and then compare it, okay. Yeah, and then so this is 2 random variables. So I am considering rolling of dice as 1, okay. See, rolling of dice is a random experiment, the sample space is 1 to 6 and the same, 1 is mapped to 1, 2 is mapped to 2, you can think of it as a random variable also, and then that is x, and then y is, that is being even or odd, okay. So now these are the die outcomes, I am taking 20 outcomes and then I am taking the indicator random variable, okay. So whenever it is 6 it is 1, 6 is 1, 6 is 1. Is this die biased die? Can you come to any of those conclusion? Think of, ponder over it, okay. And whenever it is 5 it is 0, you can think of this as the indicator random variable. And then let's verify that expectation of the indicator random variable is the probability of occurrence of that event, okay. Now let me take the number of trials that I am taking is 100,000. So I obtain 0 to 6 for 100. See, what does this mean? I just roll a die for 100,000 times and record those values. Now what is the A that I am considering? The A that I am considering is I am getting greater than or equal to 5, okay. That means the values that I can get is 5 and 6, okay. So now how many times is that, is the indicator random variable of that? You take the mean of that indicator random variable, okay. So and then and you obtain the estimated means, rolls greater than or equal to 5. Now this is the estimated expectation, this is the estimated probability, okay. I think you will be able to appreciate that. We know that expectation of an indicator random variable is the probability of that event, both of them has to be same. Now you can see that both of them are quite close, okay. This is easily you can see this, okay. So now let's go to other random variables under consideration. I am taking a binomial random variable, n is 1. So whenever I take a binomial random variable where n is 1, which is nothing but a Bernoulli trial, okay. If you want to what do you call do a Bernoulli trial, you take a binomial distribution with n is equal to 1 and p is the probability of the head which is there, and then I am taking 100,000 that means I am tossing the coin some 100,000 times, okay. And what is the estimated mean? The mean of all these samples, theoretical mean is the p itself, we know this, okay. We have, and the variance. Now how do you compute the variance for a Bernoulli distribution? It is p into 1 minus p, okay. You can compute that. So now you have obtained that and then we run this. Now estimated mean is 0.7006, theoretical mean is 0.7, estimated variance is 0.209, theoretical variance is 0.21, okay. Now whenever you have enough number of samples, so expectation variance will almost be same as that of the theoretical values is very much seen, and this is the histogram that, so you can see that we are getting 70% of the times we are getting it as the head. Now just reduce the number of trials, reduce n to 10, into 20, into 30 and try to run the same code and see will we get similar values or not, okay. Vary the number of trials and see the values, okay. Now similarly you can always this is sampling from a Bernoulli trials, okay. Now if you want from any other categorical distribution, you can specify that what are the values. Now here I want to sample cat, dog and bird. Cat has to be sampled with probability of 0.2, dog with 0.5 and bird with 0.3, okay. Now the random number generator dot choice, now these are the categories that I want, and how many times I have to sample? I have to sample it 20,000 times, and then you take the mean of each of them. Now it is seen that, so your cat is being sampled 0.196 times, dog 0.496, bird is 0.30, which is similar to what is the probability that we have assigned. Again here also change the size to a smaller value and go on increasing and see how these values are converging towards the true probabilities. Okay. And similarly we can take a binomial distribution. So this binomial distribution n, I am taking 10 and probability of success is 4, and then I am doing it, the size is 10,000 times, and we can see this here. Okay. This is number of successes. Now how many times you had a success here with 1, with 2, so okay, we get a graph like this, and then estimated mean is the theoretical mean is 4, in this case we get 3.9, estimated variance is 2.38, we get 2.4. Okay. This is again, this is for the binomial distribution. Similar thing I have done it for Poisson distribution. Since I give the code I will not go ahead with that, I have just go ahead with that. Now let us look at the continuous random variables. We will be doing the similar kind of an exercise for continuous random variable. First I am taking a uniform distribution in uniform over -2 to 3. Okay, I am sampling some 100,000 times. Now here also I am estimating the mean, theoretical mean I know what it is. Okay, so and then estimate the variance, and then theoretically compute the variance, so and then compare them. So just to see that, you can see here estimated mean is 0.5, theoretical mean is similar, estimated variance and then the theoretical variance which is there, and this is the histogram of the same. Okay. And the same thing I am doing it for the normal distribution. So ring dot normal, so this is the mu, this is the sigma which I am taking, I am sampling some 100,000 times, you get a grid. Okay. You can see here mean is 2, where theoretical variance is 2.25, and then you can see that this is whatever is in the orange line, that is the theoretical computation of the density function, and then this is the histogram, and then you see that how is it matching. So just again here also do the same thing with the same code. So now what you are supposed to do is change this number, okay, and try to run the same code and see whether you get a nice overlap like this. Okay, nice what do you call superimposition, not overlap, superimposition like this. Okay, please try it out. So similarly I have done it for exponential distribution. You can see it here, the histogram and the PDF is being what do you call nicely superimposed on top of another. Okay, and the mean, the theoretical variance, all of them are matching here. Okay. Now I want to take a couple of samples from the standard normal distribution and computes its CDF. Okay, till now I have used the PDF, I have just computed PDF. Now I want to use the CDF of it. Okay. Now it can be seen that you will get the sigmoid function. Okay. Now both the functions are important for us. Sigmoid function is quite important for us, and then we need the PDF. How am I doing it here? Okay, empirical CDF. How am I computing the CDF? Please go ahead and you should be able to obtain it neatly. Okay, fine. Okay, fine. So let us proceed. Yes, this is what I was saying. Now change the sample sizes. Okay, do it for 10, 100, 1000 and 100,000 like this, and then see how does the mean variance will be changed. Now as you can see here, now it starts from this, okay, minus 0.2 and variance is 1.56. Now our actual value is 0 and 1. Okay. Now as you increase the number of samples, the mean goes near the actual value, and then even similarly the variance. Okay. So now this is till now this is random variables. Now look at the functions of the random variables. Now how do we handle that? Now you sample x from the standard normal distribution, and then y you have, and then plot them, plot the histogram. This is the standard normal, and this is the x square of that. Okay, this is the transformation of that. Similarly, you can go ahead and look at the linear transformation. This is y is equal to x square is a non-linear transformation. Now you can think of it as you can go ahead and do it for the linear transformation, and whenever you are doing the linear transformation, now one additional thing that I have done here is, now we have taken into consideration the computation of expectation of y and the variance, and then the expected and then the estimated. Okay. So the predicted and the estimated, now you can see it here, now they are matching. Okay. So now a is minus 4, b is 5. Now if you want to find the expectation of y, now how do you do it? A into expectation of x plus b. Okay. So now a is what? A is minus 4, the mean is 3, minus 4 into 3 is minus 12, and b is this 5, minus 12 plus 5, it is minus 7. Now we get expectation to be minus 7. Okay. Around that point you should be able to obtain it. Okay. Fine. Similarly, now we are trying ahead for some discrete values. So we are taking the discrete values 1, 2 and 5 with these probabilities, and then we are computing the expectation. So we can see that they are also matching. Now similarly, you can do it for the expectation of nonlinear functions. Now if you want to find the nonlinear function, how you have to do it? Now use of lotus. Now as you can see here, this is where we have applied the lotus, okay, law of the unconscious statistician, and we can see that they are matching. See, I am giving these examples just to reinforce the formulas which are there and how to go ahead with that. Okay. And again linearity of expectations, what happens when you go ahead and use it. I have just shown it with another example. Okay. And this is a very interesting thing that I have considered. So now here x which is there is a normal 2, 3, mean is at 2, and it is having the scale of 3, and then I am making y is equal to 2x plus some noise that has been added, okay, some Gaussian noise that I have been added here. Okay. Now y is dependent on x. Now whenever y is dependent on x, and sometimes whenever y is not dependent on x, so x and y are independent, how will be the expectation gets modified is a question that I am trying to ask here. Okay. Now here you can see that, so the expectation is so here you can see that x and y are dependent. Now in that case, so expectation of xy and expectation of x into expectation of y, now you will get them as separate. On the other hand, if you have them to be independent, here I have taken x to be a normal 2, 3 and y to be minus 1 and 4. Now then you compute this expectation of xy and expectation of x into expectation of y, they are the same, indicating that these are independent. Okay, you can derive this formula very comfortably. So I have just taken, now one is a dependent random variables, the other is independent random variables. How do they work is what I have tried to show here numerically. Okay, now you can have this variance and standard deviation. So computation of variance. Now how do you compute it? So variance definition is this x minus mean of this x whole square. You can see this definition here, or alternate way. So it has to be similar, and you use the numpy and compute it. So you should get almost similar values. And properties of variance Okay. Now here y that I am taking is ax plus b, I am computing variance of y. Now what will be the variance of y? So this is one random variable ax plus b. If you take the variance, now it will be a square into variance of x. Now you can I urge you to take a piece of paper and derive this, what will be the variance of y in this case. Now we can see that variance of y and a square into variance of x, which is the actual formula, both of them is yielding us the similar numbers. Okay. So now the aim of all these what do you call simulations, what to show you that now how do you perform these kinds of computations using the libraries like NumPy and others. Okay. Now with this we conclude this section of tutorials in which we looked at the continuous random variables, we looked at the functions of random variables, we looked at the expectation, we looked at the variance and other things. So and how do you, what are the properties of expectations, what are the properties of variance, so is what we have discussed in this section of tutorials. In the next section, now what we will be going ahead is we will be taking a pair of random variables. Okay. We will be taking a pair of random variables and then we will be solving couple of problems, and similarly as we did using NumPy, we will be simulating them on the system as well and see how theoretically obtaining the value and then estimating the values with the samples now gives us similar kind of results. Now this is what lies ahead of us, and as I told you, these are what are known as just refresher discussions. Okay. Now anybody, we are assuming that the people who are the viewers of this course already know these ideas, and then this is just being repeated or this is just being reinforced. Now that is what we actually assume from the viewers of this course. Okay. Now with this we conclude today's discussion. So thank you all so for watching this section of tutorials. We will meet in the next section of tutorials. Till then, have a nice day. Bye bye.